Evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to my latest training video. We are starting to wind down the summer, and we're starting to slowly wind down the summer training series. But we're going to continue the training this evening with a lesson on atmospheric waves. Now, this topic is very important in meteorology, so I really want to take my time as we go through it together. I've divided this topic up into three parts. So this is atmospheric waves part one, and looking forward to sharing some great information with everybody. For the overview, what are we going to look at today for the atmospheric waves part one? We are going to look at the long waves in general. We're going to look at long waves in part one. From just the regular definition of what a long wave is, we'll look at long wave troughs, we'll look at long wave ridges. In part two of the atmospheric waves training, in the next video, in part two, we'll go over short waves. So we'll talk about short waves, including the major shortwave troughs and the major shortwave ridges, which are very, very important to the everyday weather we experience here at the ground. And then finally, we'll do atmospheric waves part three, which is going to cover barotropic lows, baroclinic lows. What's the difference between all of these? What's the difference between a barotropic high and a baroclinic high? So we will look at and examine all these in detail in part three of atmospheric waves. But first, let's start with part one, and we're going to talk about long waves. What do you think about here when we talk about this type of stuff is think about the atmosphere being a vast ocean of air. And it flows and contains various waves. There's various waves embedded within this vast ocean of air known as the atmosphere. Following changes in the waves helps meteorologists to predict the weather, believe it or not. Think about this. Weather is a three-dimensional science. It's not just a, hey, we live at the surface, so we only pay attention to what's going on at the surface. We must examine the atmosphere in the complete vertical three-dimension. And it starts with the long wave pattern, really. And that's really what we're going to examine in part one of this training. We'll talk about these slow-moving giants of the upper air, the long wave pattern. They guide storms. The jet stream is generally associated with this long wave pattern. I'll show you some examples of a couple really cool weather charts that help us to identify these long waves towards the end of part one here this evening. Now, these long waves are also modified by short waves, which are smaller. They're faster moving and they are more changeable waves. So these short waves are embedded within the long wave pattern, and we'll get into short waves again in atmospheric waves part two. So when we look at long waves in general, the long wave pattern is a series of troughs and ridges that circle the Earth. Now, this pattern in the long wave represents the average storm track across the Earth, as well as a general movement of these high and low pressure systems from west to east across the mid-latitudes. Now, long waves vary in their amplitude from 60 to 120 degrees longitude, and there are usually 4 to 5 long waves in the northern hemisphere at any one time. Sometimes these waves form distinct patterns. For example, in the winter season, we see distinct long wave patterns, which help us to determine which areas, if we're talking about the winter in the northern hemisphere, which areas in the northern hemisphere are going to see bitterly cold air masses when we have long wave troughs in place. Or perhaps which areas of the northern hemisphere in the winter season are going to see unseasonably mild or warm temperatures beneath a long wave ridge. So these are very important. The setup of the long wave patterns, the wavelengths, the amplitudes. This really makes a big difference in our storm system development, how high and low pressure systems move from west to east within those mid-latitude westerlies. If you live anywhere between 30 degrees latitude and 60 degrees latitude, you're in the middle latitudes. And in that particular belt of latitude is where we see all these changes in the long wave pattern, as well as short waves and kind of moving through those long wave patterns, as well as these systems, these high and low pressure systems. All right, so when we look at long waves in general, long waves are generally barotropic. What does barotropic mean? It seems like it's a fancy word, doesn't it? But really, all barotropic means is the height contours and the isotherms, the lines of equal temperature, are parallel to each other and do not cross with no temperature advection. Long waves are very slow in the way they move since they are so large in size. Look at this graphic here on the right. This really helps explain this first bullet when we say the long waves are barotropic. Now, if we look at this graphic here on the right, we're looking at the 300 millibar level. We're looking at these dashed red lines indicate lines of equal temperature. These are called isotherms. You notice how these red lines, these red dashed lines, these isotherms are separated by basically the intervals 5 degrees Celsius between each line. All right, so you notice the red dashed lines are isotherms. These dark solid lines indicate our height contours up at 300 millibars. This is at about 30,000 feet above the ground where we live, 300 millibars. And this is where the jet stream resides. So when we see this relationship of the parallel isotherms, red dashed lines, and then these solid dark lines, these height contours, and you can see the values over here on the right of the height contours, ranging anywhere from 900 decameters to 924 decameters in this example. But notice how this red dashed line, the isotherm, never crosses the solid dark lines at all. They are parallel to each other. That's the relationship. That's what makes them barotropic. And whenever you have a barotropic situation, you do not have any changes in air masses, no changes in temperature advection. Now, how do we identify long waves in general? What are the meteorological tools that we could look at? First, we could talk about satellite imagery. The long waves are usually on the backside or to the west of cloudy areas present on satellite imagery or satellite photos. Long wave ridges are usually found in cloud-free areas. Why is that? Because beneath ridges, we see sinking vertical air motion. And that means as the air sinks in the vertical, it dries out, and you can really pick this up. Specifically with water vapor imagery, you can really make out where that jet stream may be in that water vapor imagery in those darker areas or the brown areas. Depends how you enhance the satellite image with the coloring. But long wave ridges are usually found in cloud-free areas, sinking air motion due to upper level convergence with the good weather associated with them. Water vapor imagery, as I mentioned, is an excellent source to indicate where that polar front jet stream is located, and really helps you to pick out the long wave pattern by a distinctly clear zone. All right, so let's look at some of this, just break it down here on this slide. We're talking about long wave identification methods. We can use the 300 millibar chart, which is at 30,000 feet above the ground. Now that 300 millibar chart, we're going to use that in the wintertime, because in the wintertime, the atmosphere is colder and more compact and more dense. So we look at a lower altitude millibar chart in the winter at 300 millibars or 30,000 feet above the ground. Now, if we were talking about trying to identify the long wave pattern in the summertime, we would turn to the 200 millibar chart, because 200 millibars is up at about 40,000 feet above the ground. And during the summertime, the atmosphere is so very warm that it tends to expand more in the vertical as compared to the winter. And also, how do you identify long waves? It really depends on the latitude and the season. There are certain areas where we'd expect to see the long waves really setting up, specifically that jet stream, depending on the seasons and the latitudes. In the summertime, we're expecting that long wave pattern really to kind of shift to the poleward to the north across the southern Canada, northern U.S. border. And in the wintertime, we expect that long wave pattern and that jet stream to shift much further equatorward or to the south as colder air outbreaks more readily move in the wintertime. So it's very important to kind of know general average tracks of these long waves and this jet stream, the tracks of the storms. Now, the best tool to use, honestly, is what's called a 0 to 5 wave 500 millibar hemispheric chart. This chart depicts a long wave pattern with all the short waves filtered out of it. So you do have the long waves and short waves kind of together on this chart. but we're basically like filtering out the short waves. You don't even see them. It shows the true pattern uninterrupted by minor perturbations, which we call those short waves, that would otherwise distort that pattern. With long wave troughs, now let's turn our attention to long wave troughs and long wave ridges. We'll start with long wave troughs. These are elongated areas of lower heights with cyclonic curvature, or cyclonic turning of the wind across the trough axis. And they generally extend 2 to 5 miles from the top to the base of the trough. Center line of the long wave trough is center line of that lowest heights where the wind makes sharpest cyclonic curvature. This is known as that trough axis where you see the sharpest cyclonic curvature or turning of the wind. Now, when a long wave trough increases in intensity, or what we call deepening, it is basically the same as digging a hole in the ground to make it deeper. So think about deepening. Long wave trough is increasing in intensity. It's called deepening. It's like you going out to your backyard with a shovel and just digging a deep hole. That's a trough. Now, factors responsible for deepening process with long wave troughs. First thing is the approach of a short wave into the long wave trough. This short wave trough will bring colder air advection, with it causing upper heights to fall. The cold air then sinks and deepens the long wave trough. Upper level diffluence is another factor responsible for a deepening long wave trough based on wind direction as the wind spreads apart. Diffluence will cause the trough to deepen by removing mass from the air column at the top of that air column. We talked about the chimney effect in past videos. And then upstream ridges west of the trough can cause a trough to deepen. When the ridge builds west of the trough's location, it is removing mass from the trough and taking it away, and that's deepening our trough. All right, let me see. I want to see, okay, let's see. Okay, so what I want to do is I kind of want to draw this out for you. Okay, so how do these long wave troughs deepen? All right, let's just do a few drawings here. I'm going to make it pretty simple, okay? All right, the first thing first, let's say this is our long wave trough right here. This first one here, okay, approach of a shortwave trough and a long wave trough. Let's just label the shortwave trough with the letter X. All right, so as this letter X, or the shortwave trough, moves into the west side of this long wave trough, it is going to result in deepening. So you got to look at the position of the shortwave trough as it comes into that base of the long wave trough. It's going to deepen this long wave trough. Why? Because again, those short waves bring cold air advection with them, causing the upper heights to fall. Cold air sinks and deepens the trough. The other way we can look at is if, let's say, we have the wind spreading apart like this. So you notice how right at this point here, how these height contours are closer together. But as we get further this direction back here, these two red lines are moving further apart. And that's called diffluence. And that is removing mass. Remember, we talked about removing mass at the top of the air column. So here's our air column. Here's the surface. Here's the air rising. Air converges here in the low levels. I don't know why it's doing that, this pen tonight, but anyway, you get the point. We're removing mass up here at the top of the air column, and then that's resulting in more accelerated low-level convergence and rising air to make up for the loss of mass up the top of the air column. So that will deepen the trough. And then again, this one's interesting, the last one again, because we're talking about the upstream ridge. So let's just do a ridge and a trough, okay? So this right here will be a ridge, R, and this will be your trough, T. Now, what can happen is sometimes is this ridge here can actually build. So let's say now the ridge is way up there like that. That's going to cause that downstream trough over here, T, to deepen. Okay? So as this ridge amplifies or builds, those heights continue to rise at this location, it's going to cause the downstream effect of the trough to deepen. So I just wanted to explain these three mechanisms a little bit with drawings. Here's the example with a short wave really causing this long wave trough to deepen. This little solid black line here represents your short wave trough. And these three solid black lines, this represents your long wave trough. So you got your little, I'll label this SW here. This is your shortwave trough here. And as it moves through the base of the long wave trough, this long wave trough is going to deepen or dig further. And this is the example of the after. See how much more deep this trough is compared to this picture on the left? And that's just because of the influence of the shortwave trough and that cold air advection really in the backside of the long wave trough, digging that trough down. All right, additionally, what we call for long wave troughs, we call them, if they're weakening, we call that filling. Long wave troughs may fill by the following. You will find out in meteorology, by the way, that there's a lot of opposites. So if you learn one thing one way, just do the opposite of the other, and you usually are pretty good. So for now, we're talking about filling or weakening of a trough. What does that mean? Let's say this is my initial trough. Now we're saying this is my trough. So this is the initial trough. See how deep it is here, how much it's digging? And then it becomes this right here, where it's not as deep. So we have a shortwave ridge that moves into the long wave trough axis. That brings warm air advection. We don't want that for a trough. This causes heights to rise. That trough is going to fill because we're basically adding upper level convergence to the column. More mass to the column when the heights rise. Confluence aloft, that's based on wind direction as the wind comes together. It can cause filling of the trough. You're again adding mass to the top of the air column. So an example of confluence is when two wind directions kind of blow towards each other. All right, so let's say initially you're here at point A. See how far apart these two lines are, these two red lines are at point A? And then by the time you get to point B, right here, look how closer these lines are together. This is called confluence right here, where those height contours get closer together. The wind direction is kind of converging the upper levels of the atmosphere, and that's going to add mass to the column. That's going to result, when you add mass to the top of the column, that's your damper effect. Upper level convergence leads to downward vertical motion. And at the surface, you have low-level divergence. So this is associated with fair weather over here. That's also going to weaken your long-wave trough or fill it. Long-wave trough movement now. It can be predicted by looking at possible intensity changes. Long-wave pattern moves from west to east, follows the wind flow in the mid latitudes. If the trough deepens, it tends to grow larger and will slow down. If the trough fills, it will decrease in size and speed up. And the speed of movement of long wave troughs is generally ranges from slow, less than 4 degrees longitude per day to the east, to it can also remain stationary in the long wave pattern, the long wave trough, to possibly even retrograding, which means it's moving backwards or westward. So there's a lot of interesting thoughts on this slide as far as long wave trough movement. You got to look at this intensity change here. Okay, got to look at that first. Long wave pattern again moves from west to east. If the trough deepens, so let's take a look at this. If the trough deepens, it moves slower to the east. All right. If the trough deepens, it moves slower. But if the trough fills, it moves faster. So this would be a deeper trough. It's going to move slower, D for deeper. And this is a weaker trough. It's going to move quicker. All right. Again, there's their speed of movement. Now, these things, when we talk about stationary weather patterns, you could have a very stuck pattern, so to speak, with the long wave pattern where there's really hardly any movement. And it actually can become stationary, or it can actually move backwards towards the west. Now let's talk about long wave ridges. Now, they're an elongated area of higher heights, extending 2 to 5 miles from the base to the top of the ridge and having anticyclonic curvature. You remember from previous videos when we talked about ridges, it's upside down shaped U. The center line of the highest heights right in here where you reach the highest point, that is known as the ridge axis. That'd be right here. The ridges are going to build or get stronger via the following processes. If you get a short wave ridge moving into the long wave ridge axis, this is going to bring warm air advection. That's going to cause your heights to rise, and that's what we want for a building ridge. So you get a shortwave ridge, you get increasing confluence aloft, which adds mass to the ridge, and indirectly by the deepening of a trough upstream from the ridge axis, usually to the west. As the trough deepens, it removes mass from the trough. The removal of mass from the trough is then added to the ridge. All right, so those are the three ways we can actually build these ridges. All right, you can start first with a shortwave ridge. All right, let's just say this is a shortwave ridge right here at this point, and it's moving up into the long wave ridge axis. This will cause that ridge to get taller and build. Additionally, the confluence aloft, which makes sense because that's that damper effect, upper level convergence, is going to result in sinking air motion, and that ridge is going to get stronger. And then indirectly by the deepening of the trough upstream to the west. So let's say initially your pattern looks like this. This is your trough and this is your ridge. And then let's say it goes to this. Let's say that trough to the west really deepens like this. This ridge is going to also build downstream like that. So hopefully that makes sense. Ridges are weakened via the opposite processes, really. You get a shortwave trough moving into the ridge axis that brings cold air advection into the ridge, and that's going to result in lower upper heights. And the ridges just don't want that. In order for an upper level long wave ridge to build, it wants warm air advection. The diffluence, the wind direction spreading apart, or those height contours spreading apart, aloft will remove the mass from the ridge and weaken it as well. And then indirectly, long wave ridges will weaken by the adjacent trough filling, taking mass out of the ridge into the trough. Here's an example of the shortwave ridge. That zigzag line here represents your shortwave ridge, moving up and into the long wave ridge here. That is going to result in a building ridge. Look how much taller this ridge is on the right compared to this ridge on the left. The before, that ridge is not nearly as tall as compared to the after. When we have that shortwave ridge come on in to the long wave ridge axis, it's going to result in these higher heights building. Now, long wave ridge movement, by knowing the intensity trend of the ridge, just like with troughs, the movement can be predicted. The speed of movement of a long wave ridge ranges from slow, generally less than 4 degrees longitude per day to the east, to stationary, to possibly retrograding, backing up, moving west. Now, if the ridge builds in intensity, it will slow down due to its increased size, and as the ridge weakens or flattens out, it will become smaller and speed up. All right, I'm going to go back here in a moment, but before I do, this is my last slide of Atmospheric Waves Part 1. What charts do I use to analyze long waves? All right, so let's take a look at this. We have on the left, we have an example of the 300 millibar chart, and I mentioned this earlier, we want to use that in wintertime because the atmosphere is colder and more compact. The black solid lines here outline your long wave pattern, by the way. So we're looking at 300 millibar chart, 30,000 feet. These black solid lines outline your long wave pattern as well as your jet stream axis, your polar front jet stream axis on this chart. So we generally look at the wind speeds and on these kind of charts and analyze them and kind of see what the wind speeds are. But you really see a couple features here. You see a long wave trough here. We can look at a long wave ridge here, a long wave trough in the Midwest. Then you have a ridge at that location. I'm sorry, not a ridge. That's a trough. Ugh, I messed that one up. Let me erase that. I apologize for that. Okay, oops. Let me do this again here. I'll go ahead and erase that one here. Let's reanalyze that correctly. All right, so this right here would be a weak ridge. And then you have the long wave trough here, and then a much more higher amplitude ridge there to the northeast. So you can look at these long wave charts and identify, hey, where are my ridges, where are my troughs in this long wave pattern. In general, you're going to have better weather with ridges, and you're going to have more stormy weather with these troughs. And then over here on the right, this is a 200 millibar chart in summer. We use that because our atmosphere is much warmer and more expansive. So we want to use this chart in the summertime, 200 millibar chart. These hashed areas here indicate the general jet core or the highest wind speeds. Here you can see a ridge. See that upside down U shape. This, you can see a trough back here. And that's it. All right, that wraps up my training video, Atmospheric Waves Part 1. These are very important, long wave troughs and ridges. This long wave pattern is very, very important. This really determines what kind of weather we're going to have at the ground where we live, whether it's going to be cold and stormy or warm and dry. Beneath long wave ridges, you're going to be warm and dry, and within the troughs, the long wave troughs, you're going to be cold and stormy. So it really is important to take a look at long wave troughs and ridges. We kind of went over the mechanisms for deepening of long wave troughs or filling of long wave troughs or weakening of them. We looked at the movement of long wave troughs. Just realize that the speed of movement is going to range from slow to even stationary to possibly retrograding back to the west. If the trough deepens, it tends to grow larger, it will slow down. If the trough fills, it will decrease in size and speed up. We talked about long wave ridges, and we talked about the different things that strengthen long wave ridges and also weaken long wave ridges. And then we looked at the different types of charts we can use to analyze long waves, from the 300 millibar chart in winter on the left to the 200 millibar chart in summer. All right, that wraps up the training video tonight. I certainly hope you got something great out of it. This is, again, a very important concept in meteorology. I can't say it enough. This long wave pattern really steers storm systems. You'll learn more in part 2 here on short waves, shortwave troughs and ridges, okay? These are the true enhancers of vertical rising air motion in the atmosphere and really, really allow storms to get very strong and also high pressure to get strong as well, or, these surface lows and highs. They rely on this connection to these shortwave troughs and ridges. And so we will go into this in the next training video, and then we'll conclude by looking at the differences between baroclinic and barotropic lows and highs. That's all I got for now, everybody. I hope you enjoyed this great, great training video. Until next time, everybody, take care and God bless.